All right, welcome back. Today we are diving deep into a really fascinating material called core spun yarn. Now, this is not your everyday run-of-the-mill thread, no way. Think of it more like a high-performance hybrid, a piece of serious engineering that takes the best properties from two completely different materials and fuses them into one, well, perfect strand. Let's get into just how clever this bit of textile engineering really is. So here's our roadmap for today. First up, we're going to nail down what exactly core spun yarn is. Then, we'll take a peek inside the factory to see how it's made, and we'll get into the 5 key variables that engineers have to get just right. After that, we'll see this stuff in action in one of the most extreme jobs you can imagine for a thread. And finally, we'll follow its path all the way from raw yarn to the finished product you'd find on a spool.
Okay, let's start with the basics. Section 1, what is core spun yarn?
You know, the easiest way to think about it is like an armored gable. Seriously, you've got that strong, functional inner wire. That's the core, and it's what gives the yarn its main superpower, whether that's incredible strength or maybe elasticity. And then wrapped all around that core for protection is an outer layer, the sheath. This sheath is what brings in other qualities, like comfort against the skin, or heat resistance, or just a nice texture.
And this image here just lays it all out perfectly. You can see it, right? That central piece is the core filament. That's the backbone of the whole thing. And then, look how those outer sheath fibers, which are cotton in this example, are spun in this perfect spiral right around it. It's this two-part construction that's the secret sauce, giving the yarn all those special properties.
Okay, so we know what it is. The big question now is, how do they actually make it? Well, there are a few different ways, but we're going to zero in on the most common and, frankly, most economical method: ring spinning.
So here's a look at the machine itself. Check out the 2 separate feeds coming in on the left side. You've got the core filament that's being pulled from one spool, and then you have the sheath fibers, which start out as this thick, fluffy rope called roving. They're fed in from a different spot. They actually follow 2 totally different paths until they meet up right at the drafting system. And the whole process is really like a beautifully choreographed dance. The core filament is fed through a guide, kept under just the right amount of tension. At the same time, that fluffy roving of sheath fibers gets stretched and thinned out. Then, and this is the magic part, they meet at the exact right spot, and a super fast spindle twists the sheath fibers tightly around that core, basically locking everything together into one unified yarn.
All right, now we're getting into the pro-level stuff. This is where the real engineering comes in, the details that can make or break the final yarn. To get the performance you want, you have to control a bunch of key variables. And trust me, if you want to understand why one core spun yarn is great and another one fails, this is what you need to know.
So there are 5 major variables that really affect the final product. You've got the core sheath ratio, the pre-tension on the core, the spinning draft, the number of roving feeds, and finally the twist. Let's tackle each one of these.
First up is the core to sheath ratio. And this is a classic engineering balancing act. You could go with a 2-to-1 ratio, so twice as much core as sheath. Yeah, that might make the yarn stronger, but the downside is you get really poor coverage, and that sheath can literally just strip right off during use. That's no good. For a tough job like sewing, a balanced 1-to-1 ratio gives you much better coverage and durability. It's just better.
Next up, pre-tension. And this one is all about control. This quote really nails it. If insufficiently tensioned, the filament will either periodically appear at the yarn's surface, grin through, or become wrapped around the fiber ribbon. Grinning through, that's the industry term for when the core peeks out. It looks terrible, and it means the yarn's integrity is shot. You get that wrong, and the whole thing is a failure.
And get this, the amount of tension you need depends massively on what the core is made of. This chart is pretty eye-opening. For a simple flat filament, you only need to stretch it about 5 to 10%. But look all the way to the right. For an elastomeric core, like you'd find in stretchy jeans, you have to stretch it up to 400%. That's insane, right? But you have to do it so that when it's all done, the core retracts and stays completely hidden inside the sheath, ready to provide that comfortable stretch.
Okay, the last 3 variables kind of work as a team to get everything just right. You've got the spinning draft that basically controls how thin the sheath fibers get stretched, which sets the final yarn's thickness. Then there's the roving feed, which is all about positioning, making sure that core ends up dead center. And finally, you have the twist. Think of the twist like a super strong glue or a clamp that locks those sheath fibers in place so they can't go anywhere.
Okay, I know that was a lot of technical detail, but why does all this precision matter so much? Well, let's look at a real-world example where this yarn is put under the most extreme stress you can think of, high-speed sewing.
First, just consider the speed. A sewing machine needle. It accelerates to over 180 kilometers per hour. That's just nuts. Every single time it punches through the fabric, it hits that speed.
And it's not just a one-time thing. That insane cycle of speeding up and slowing down, it happens 120 times, every single second. The amount of stress on that little piece of thread is just unbelievable.
And then there's the heat. All that friction makes the needle get incredibly hot. We're talking up to 360 degrees Celsius. That is hot enough to melt a standard synthetic thread the instant it touches the needle.
So here's the problem, right? A pure cotton thread just isn't strong enough for that speed, and a pure synthetic thread would just melt from the heat. So what do? Well, this is where our core spun yarn becomes the hero. You get the best of both worlds, a super strong synthetic core that can handle the mechanical stress, wrapped in a cotton sheath that acts like a heat shield. It's the perfect solution.
All right, for our last section, let's follow this amazing yarn through the final steps of its journey to see how it becomes the finished sewing thread you'd buy in a store.
This chart lays out the entire manufacturing process, from start to finish. We've already covered the core spinning part. After that, it goes through a bunch of steps. Doubling, heat setting, dyeing, lubrication, all before it gets wound onto a spool. We're going to zoom in on two of the most important post-spinning steps, doubling and heat setting.
Okay, so after it's spun, the yarn goes to a process called doubling. All that means is they take 2 or 3 of these individual yarns and twist them together into a single, stronger thread. And this step is absolutely critical. It locks those outer sheath fibers on even tighter, which gives the final thread incredible abrasion resistance. It needs that to survive being yanked through the eye of a needle thousands of times.
And the last key step is heat setting. See, you've got 2 different materials, the synthetic core and the cotton sheath, and they shrink and react to heat differently. This creates a kind of internal stress in the thread. So they steam it under pressure, and this basically lets the whole structure relax and stabilize. It's kind of like therapy for the thread. It gets rid of all that tension and makes sure the final product is stable and won't snarl or tangle up on you while you're sewing.
When you step back and look at it, core spun yarn is just a fantastic example of what we call composite engineering. It's the idea that by combining 2 different things in a smart way, you get something that's way better than either of them could be on their own. It really makes you think, right? What other hybrid materials are out there solving problems we don't even know about?